So what we're looking at here is the Henderson-Hasselbalch equation for ABG analysis, and this is just a quick review. So pH is determined by pK minus log times 0.03 times PaCO2 divided by bicarb. However, it can be reworked, so it's pH equals 6.1 plus log times HCO3 divided by 0.03 times PaCO2 if you go into the fancy mathematics, but that's not for us. For us here, what we're interested in is the part of the calculation where you can input the sodium bicarbonate and you can input the PaCO2 from the patient, so that way you can figure out what you want to do. So let's switch over to the pure data sketch, and we'll see that there's quite a bit going on here, but that's fine. We'll just look at it real quick. So we have on the left hand side the PaCO2 slider, and you'll see it going up. Let's just make only this come up and down. And you'll see that as this goes up and down, the value right here will go up and down as well for the PaCO2. So we have right here an ideal zone, which is between 35 and 45, and our normal ranges are listed right over here as well, if you want to just read along or follow along. Everyone has their own normal ranges, so these are the ones I'm using today. The ideal zone is, the area that, we most commonly are not really worried about anything. Yellow being I'm getting up and inspecting to see what's going on. And anything in the red area, I need to figure out what's going on immediately for a patient, and we need to start addressing the situation right then and there. So you'll see that this is not equal on both sides. When things go lower, we get more concerned quite rapidly because we can only go down so much. But, the CO2 values can climb astronomically high. So the other side, being greater than 100 is something you can see. So we do factor it in. And then we do the same thing over here on the bicarbonate side. So the same color values, green, yellow, red. Now, the interesting thing is on the sliders, if we change the bicarbonate, it doesn't change anything on the screen. If we change the CO2, it changes everything on the screen. So just keep that in mind. Now, with the two values that we pick, it will feed into the Henderson-Hasselbalch equation. So here it is again, where bicarbonate is divided by the product of PaCO2 being multiplied by 0.03. So we have that over here in the pure data sketch, where the bicarbonate feeds into one part of the equation, and the PaCO2 feeds into the other part of the equation. The PaCO2 in this one is feeding into the money sign F1, and the bicarbonate is feeding into the money sign F2. So if we look back at the equation, we can see bicarbonates on top being divided by the product of 0.03 and PaCO2. So we can see that that's occurring in this box with those two values being plugged in, and then we get the value from that. Now that gets sent as step 1 over to the next portion where we can see it comes out again as 20.4 for these values right now. And then it performs the function of log, and we're not going to get into that, but I double checked this and triple checked this, and it's working appropriately and giving accurate values compared to my calculator. You can follow along and plug it into yours if you want to. And I just added the 6.1, and then we get our pH value, which in this case is 7.409. Now that gets displayed in 3 different ways. We have our first being in bins, where when a value falls within a certain number range, it will go into its specific bin. So we can see as we go beneath 6, it will go into the bin of 6, and vice versa for bin of 8. Cool. Now we can also see a zoomed in view where it's presented as a horizontal slider, and then beneath that as a very much zoomed in slider to see the ideal zone and how narrow it is compared to other values outside of the ideal zone. The ideal area for a human being when it comes to pH is exceptionally small, especially when you're looking at the entire scale of pH. Our ideal zone is very, very narrow, and the body is able to compensate for it in very, very interesting ways, to say the least. So here's the equation again. Here is the sketch again, and then we'll just play with a couple of values. So let's go to concern and keep the bicarbonate normal. And we can go through the equations and see that gives us a pH of about 7.27. Now, as the CO2 increases, we can see the pH naturally decrease on the horizontal slider. And if you wanted the definite value, you could see the calculated value as it goes down from the CO2 going up. A very easy way to demonstrate the relationship of CO2 to pH and how they are inversely related. As the CO2 goes up, pH comes down. As the CO2 goes down, pH goes up. If we did the same with bicarbonate, we would see that that relationship is a lot harder to see here because it's coming into this cold section of the equation. So then we have to kind of click on the CO2 slider to see what it would be here. But we can see that it would go down. If we do it again, it would go up. So bicarb goes up, pH goes up. Bicarb goes down, pH goes down. Pretty interesting stuff. But a definite relationship that a respiratory therapist must be able to appreciate, because the one thing that we will explore in the next video is how CO2 is related to the respiratory rate. So as a patient breathes more, the CO2 will come down, which is an interesting mathematical relationship as well. So here's the H&H equation, and here's the sketch. Equation, sketch.